Hey everyone, welcome to Seabird University. We will give just a minute or so for people to trickle in from the waiting room. Right. Welcome to Seabird University 2024. My name is Nicole Lucas. I'm with Seabird's marketing team, and I'll get us started with just a little bit of housekeeping before we get into the real presentation. Marialena will take it away and give her whole presentation on the HydroCAT and the Lahaina case study, and then there will be some time for Q&A after. You can all enter your questions through the Q&A box there at the bottom of your screen, and we will answer them after the presentation and then make them visible to the rest of the audience. If you have any issues with sound or anything, any technical issues, feel free to pop those in the Q&A or raise your hand and I will work with you to try and get those sorted. I think that should cover most of everything. The presentation will be recorded, so if you have to hop out early, don't worry about it. It will be available on our YouTube channel probably within the week. And with that, I will pass it off to Marialena.
Okay, thank you very much, Nicole. Welcome, everyone. Let me share my screen first. Okay. Sorry. Okay. You can see my screen now, right?
Yes, it's the, you might want to put the presenter view. There you go.
Okay, perfect. Let me actually, just give me 1 second, always some technical, okay, no. Okay, so thank you, Nicole. Welcome, everyone. Good morning, good afternoon, or good evening, wherever you are. Thank you for joining us today on this Seabird University session, where we'll be talking about how we can use the HydroCAT-EP V2, the multiparametric CTD, to monitor coastal environments and ecosystems. Before we dive into today's topic, I would like to take a minute and introduce myself. My name is Marialena Christopoulou. I recently joined Seabird Scientific, the team here in February 2024, and I'm very excited about that. My current role here at Seabird is customer support scientist in physical oceanography. I'm originally from Greece, so I have a background in geological and physical oceanography. I'm originally from Greece, so I did my bachelor's and my master's there. And in 2019, I came in the US to do a PhD in Southern Ocean Paleoceanography and Climate. I have worked with Seabird CTD data from the Aegean Sea during my years at the University of Athens after I finished my master's. And so here I am now, very excited to give you a presentation on the HydroCAT-EP V2 and the Lahaina case study. So for today's presentation, I will start by describing some important and unique characteristics of the HydroCAT-EP V2, but really where I will be focusing on is a study we performed in collaboration with the University of Hawaii at Manoa to monitor the impact of the 2023 wildfire in Lahaina in the marine environment. I will present the deployment and the recovery of the HydroCAT-EP V2, as well as some of the preliminary data acquired during the deployment that demonstrate the capabilities of the instrument in monitoring water quality. So Seabird has some very widely used lines of moored instruments. One of them is the MicroCat. I think that this is a very well-known line of moored instruments, also known as 37s. These are, of course, sensors that can be deployed in fixed locations and left there for certain amount of times, depending on the application, to record temperature and conductivity, of course, as well as optional pressure and dissolved oxygen over long time intervals. The HydroCAT-EP V2 was in a way born from this line of sensors, the 37, and is a very powerful multiparametric CTD. I like to call it the Swiss Army knife, as you can measure a number of different parameters with only one instrument. It has, of course, a temperature and conductivity sensor, like all seabird CTDs. It also has an optional pressure sensor, dissolved oxygen, turbidity, and chlorophyll. What is in particular unique about the HydroCAT-EP V2 is that it has an integrated field swappable pH sensor that was specially designed for it. So the HydroCAT-EP V2, with its compact package, advanced design, and expanded capabilities, can be used in a number of applications, such as estuaries, lakes and reservoirs, rivers and streams, and of course, marine environment, coastal marine environments. Okay, so lots of different sensors that are integrated in the HydroCAT-EP V2, and I would like to take a moment and just briefly describe a little bit about the specs and calibrations. All sensors in HydroCAT-EP V2, except for the pH sensor, have a 1-year factory calibration. Seabird in general recommends a yearly calibration of all CTDs in our facilities to maintain their higher performance and their high accuracy. The pH sensor is a glass electrode pH sensor and requires a 90-day field calibration. You can basically have multiple of these sensors, calibrate them in the lab, and then go and replace them in the field. The accuracy of the pH sensor is 1.1 pH and can retain its stability for 90 days. So keep that in mind, that in general, the main limiting factor of deployment time is the pH sensor here. Additionally, the HydroCAT-EP V2 has an optical sensor that can measure chlorophyll and turbidity, and is basically a small eco-FLNTU for those of you who are aware of the seabird eco sensors. And also, the oxygen sensor is the seabird oxygen 63 sensor that is an optical dissolved oxygen sensor. So as most of seabird instruments, CTDs, of course, the HydroCAT-EP V2 has the unique pump technology. The signature, I would like to say, of the seabirds CTDs. What this means is that water is pulled in the flow path and where a pump connects the temperature, conductivity, pH, and dissolved oxygen sensor. And every sampling interval, every few minutes, water is pulled in the flow path. And so all these 4 parameters are measured in the same parcel of water. This controlled flow rate matches the time response of the different sensors and generates the most accurate raw data, something that it is also very important for further calculation of parameters such as salinity. Some other technical information, HydroCAT-EP V2 has an RS-232 and SDI-12 interface. It can be deployed with internal batteries, lithium batteries, as well as external power, and comes with its own software, the UCI, that can be used to calibrate your pH sensor, check your sensor and your data that are currently recorded. It has a deployment wizard, and you can, in general, change settings and adapt your deployment with this software. It's very easy to use, and it can be found and downloaded from our website. Okay, let's go to the most the part of the case study that is very useful to understand how the HydroCAT-EP V2 really, as I like to call it again, is a Swiss Army knife, because you can measure all these different things with one instrument and for very good time intervals. First, I would like to say that, of course, coastal environments are very dynamic and sensitive. Human activities directly affect them. Because we interact so much with coastal environments, activities such as tourism and urbanization and land use can affect the health of coastal ecosystems. but they can also be affected by climate change, which is also, of course, human-induced, but is in a larger scale, let's say. So, for example, increasing CO2 in the atmosphere, it is absorbed by the ocean and coastal environments, affecting the chemistry, causing ocean acidification. One of the main consequences of global warming and increasing drought is wildfires. Wildfires are increasing worldwide and become more and more severe. And even though they're very well studied, I would like to say, in terms of its impact in air quality and land, their impact in nearby coastal environments is not very well studied. And different pollutants and other contaminants, toxic elements, can be transferred from the burned areas when they are proximal to a coastal environment and affect, again, chemistry, pH, oxygen levels, biological productivity, and more. So in August 2023, one of the deadliest wildfires in the history of the US burned over 20,000 acres of land and over 2,200 structures in Lahaina, while over 100 lives were lost and more than 10,000 residents were displaced. The wildfire in Lahaina was the first urban wildfire proximal to a coral reef. Strong winds during this time and drought conditions created all the, I will say, not like the ideal circumstances for this wildfire to spread rapidly and cause all these devastating damages. So after the wildfire, one of the goals of scientists from the University of Hawaii at Manoa was to understand the potential impact of terrestrial runoff on the biogeochemical and oceanographic parameters at the Kahoma Stream mouth, a major runoff outlet in Mala Wharf. Seabird partnered with the university and Dr. Andrea Kealoha, shown here, assistant professor at the Department of Oceanography, along with Dr. Craig Nelson, Dr. Nick Hoko, and Dr. Eileen Nally. Seabird loaned the HydroCAT-EP V2 CTD to Dr. Kealoha and her team to monitor coastal water quality of Lahaina after the fire. Our very own product manager, Natalie Zelinsky, traveled to Lahaina during this time and worked with the team there to deploy and recover the instrument, making sure that everything went smoothly. Okay, so the deployment. The HydroCAT-EP V2 was deployed on November the 12th of 2023, approximately 14 weeks following the Lahaina wildfire, where you can see the blue arrow is the outlet, the Mala Wharf outlet that I mentioned earlier, where all the runoff outlet is, and all the terrestrial runoff comes from the burned area. Given this site regularly experiences large debris deposits, such as tree trunks and branches carried down by the stream, the instrument was deployed in a cage to prevent physical damage. The cage was bound to the top of 2 cement blocks for stability, as well as to prevent interference from debris. Additionally, on the right picture, you can see people from the University of Hawaii installing a surface buoy marker so that the cage can be located from above water. And I would like also to add here that this HydroCAT-EP V2 included all the sensors that can have, like all the optional sensors: conductivity, temperature, pressure, dissolved oxygen, pH, turbidity, and chlorophyll A. So in biologically rich environments, as the Lahaina coastal environment is, it is typical for biofouling to occur, especially during the first weeks and if the deployment lasts more than a few days, of course. For example, here in this image, you can see we are 1.5 months within the deployment, where significant growth all over the cage has occurred, and in the instrument. The HydroCAT-EP V2 has different anti-fouling measures, ensuring stability of all the measurements. Here on the right side, you can see the optical sensor, turbidity and chlorophyll, remaining clear due to the integrated copper faceplate and the wiper that cleans the sensing window at every sampling interval. So the instrument was finally recovered February 1st of 2024, 3 months after the initial deployment, after sampling its parameter every 20 minutes, resulting in a little less than 6,000 total measurements per parameter, or a little more than 40,000 measurements in total. And here is a time series that were created by the instrument. I think this is always for sonographers, for scientists, and for technicians in general, the most interesting part, looking at the data. So here's the 3-month time series from top to bottom. We have temperature, salinity, chlorophyll, turbidity, oxygen concentration, oxygen saturation, pH, and pressure. The x-axis is the whole deployment interval from the left to the right, from the beginning to the end. And the two vertical lines mark December 1st and January 1st. Overall, the instrument captured 3 months of continuous data of all parameters. At the bottom, we can see the fluctuations in pressure that are characteristic for the tidal dynamics in the region. Baseline conditions were captured for temperature and salinity, with a prominent decrease in salinity in early January, here where you can see the arrow. So right after January 1st, and with a progressive gradual decrease of temperature due to getting into the winter months, we observed that the instrument capture a prominent decrease in salinity. The optical sensors also recorded 2 abrupt increases in the beginning of January as well in both chlorophyll and turbidity that largely correlate with this salinity decrease. Oxygen dynamics mainly are driven by the tidal fluctuations, while the pH variability ranges from 7.5 to a little over 8, with a gradual decrease post-January. We will focus here a little bit on the January event. So this is the same data time series that we saw in the previous slide. However, this is only January, and it will focus on the salinity decrease observed in the beginning of January. So this low salinity event correlates to a heavy rainstorm that took place in the region on January 8th. So increased rainfall, over 90 millimeters of water that was that took place during this time in Lahaina, might have caused this decrease in salinity. The turbidity and chlorophyll peaks are also synchronous with this event, and according to more data that were collected, have been collected through water samples and other data that were collected from the University of Hawaii at Manoa and Dr. Kealoha's team, there have been shown there was some increased concentrations of nutrients and metals, as well as microbes associated with hydrocarbons, and some sites showed some moderate hypoxia. So overall, this increased rainfall, this rainstorm event might have caused the salinity to decrease in this region. The instrument was deployed in approximately 3 to 4 meters depth. So we are in a shallow environment. And so the decrease in salinity might have been caused by the rainfall, as well as the turbidity and the chlorophyll bloom might have been caused by debris and nutrients coming into the marine environment from the burnt area, although further investigation is needed. The gradual decrease in pH is still, again, under further investigation by the team from the University of Hawaii at Manoa. There is always a possibility that because we are towards the end of the 90-day field calibration period, stability period, there might be a chance that this is a gradual shift of the pH sensor. However, with increasing pollutants coming into the marine environment and increasing biological productivity, we might have a regional decrease in pH due to respiration of organic matter. To summarize our findings and our today's talk, the HydroCAT-EP V2 is a powerful multiparametric CTD that can record high-quality continuous data in a wide range of environments. Parameters that can be measured include temperature, conductivity, pH, dissolved oxygen optional, pressure, turbidity, and chlorophyll also optional. It is equipped with a field swappable pH sensor. The HydroCAT-EP V2 was used to monitor the water quality after the Lahaina wildfire in Lahaina and capture 3 months of continuous data. Both baseline conditions and flash events, short-term events, can be observed in the time series that were created from this case study. Thank you so much for watching today's presentation, and I'm happy to take any questions.
Thank you, Marialena. If anyone has questions, please go ahead and put them in the Q&A box at the bottom, and we will start answering.
I see there is.
Maybe you did such a good job of it explaining everything. There's no questions.
I want to say here that these are preliminary data, and there is a lot of further analysis that is currently conducted by the University of Hawaii at Manoa. And so we are very grateful for this collaboration. And this is, our main we care at CBIRD, we care a lot in collaborating with scientists and research projects and providing the means to better understand what might be happening due to, any kind, from baseline conditions to any disturbances. So yeah, that was a very interesting study.
Looks like we have a couple of questions. Mallory is interested in hearing a bit more about routine sensor maintenance outside of the 90-day pH calibration. Is that something you can speak to?
Yes, I would. I can say for sure that outside, so for the whole instrument, right? Not just for the pH sensor. For the CTD or for the pH sensors?
Okay. For the whole sensor.
The whole sensor, okay. So the whole sensor is CBIRD in general recommends that for after a year, the instruments have to be returned to our facilities at CBIRD in Bellevue and be recalibrated in our baths. In terms of maintenance, any cleaning of the sensors, in general, the biofouling is taken care of by the biofouling TPTO cartridges that are very small amount inside the flow path. And so it is we make sure that the flow path remains clean from biological growth due to these TPTO cartridges. But overall, some basic maintenance while the instrument is deployed, and then every year recalibration in our facilities.
We have another question from Ahmed. I think he's asking, is the deployment similar to that of a CFOX? But correct me if I'm wrong.
I don't know the answer to that, so I would have to talk with if that's okay, I could reach out to you after this session and answer this question with a little bit more better information.
Good. We have someone asking how DO is affected by water runoff and other pollutants, and can it be correlated to turbidity increase or decrease?
Yeah. So any input of all these processes and all these parameters are interconnected in general in coastal environments and in the ocean in general. So turbidity is a measure of how clear is the water column, right? So if you have suspended material or if you have input of any terrigenous material, you start having more muddy waters, as we call them, and you start having less light. The processes, the interaction, and the feedbacks that happen between all these parameters are not always so straightforward. So you don't have something that increases and something else necessarily decreases. So you can have input of terrestrial material coming in the seawater that, on one hand, might decrease the visibility, and so light penetration might not be as optimal for photosynthesis. At the same time, increase of nutrients coming in from this material might enhance productivity. And any change in productivity balance, in any biological productivity balance, can in turn affect oxygen levels. Right, because increases of biological productivity on the surface increases oxygen levels on the surface. However, sinking of any biological material and degradation of organic matter will decrease oxygen levels. So of course, it's very, very complicated and has to do with different time scales and regional patterns. But this is why a multiparametric approach helps to better understand the whole picture. You have to have a lot of different parameters of the same system and understand what happens in both long-term and short-term time scales to have a better understanding of how any stressors might affect the environment.
Anyone else have any questions? Definitely put them in the Q&A. We have someone asking if the oxygen sensor can be constant, maybe consistent for more than 3 months.
Yes, yes. It is the oxygen sensor as well as the rest of the sensors, except for the pH sensor, have calibrated and stability for 1 year.
And someone is curious if we have a ballpark for how many of these systems have been built and deployed so far.
Oh, that's a very good question, actually. That will make me ask our product managers, and I'm happy to get back to you.
Give one more shot for anyone to ask any other questions. All right. Well, I think that might be all the questions, but if anyone else has any questions that come up later, you can always reach out to Seabird. And this, as I mentioned earlier, this will be recorded or is being recorded and will be posted on our YouTube channel. So keep an eye out for that. You also will all be getting an email with links to some follow-up surveys. If you could take a couple of minutes to fill those out, giving us your feedback on this year's SBU sessions and ideas for future sessions. If there are any topics you'd like us to cover in the future, we really value your feedback, and that helps us make decisions about what kind of presentations to create moving forward. But with that, I think we can call it a little bit early. And thank you, Marialena, and thank you everyone for attending.
Thank you. Thank you so much, Nicole, and thank you everyone for being here today.
All right, take care.